types of data. So we have some basic types of data being a parameter or a statistic. A parameter is a numerical measurement describing a population, and a statistic is a numerical measurement describing a sample. And sometimes it's nicest to see these as mnemonics. So a parameter goes with a population. So population parameter, both start with P. Likewise, a statistic describes a sample. So sample statistic, both start with an S. An example of finding a statistic versus a parameter is this example. There are 17,246,372 high school students in the United States. In a study of 8,505 United States high school students 16 years of age or older, 44.5% of them said that they texted while driving at least once during the previous 30 days. Based on data in texting while driving and other risky motor vehicle behaviors among United States high school students by Olson, Schultz, and Eaton in the Pediatrics, Volume 131, Number 6. And we want to know, is this a statistic or a parameter? Since this 44.5% of the students from that 8,505, this would be a statistic. And that's due to the fact that it describes the 8,505 high school students. That was 16 or over, which is our sample. And it makes no note of it trying to apply it to the population. Our population is the 17,246,372 high school students. So now some data types. We could have a quantitative data, or numerical. That's where numbers represent counts or measurements, or units. A discrete quantitative variable is a finite or countable number of values. You could count them, even if they are very large or if they're very large, specifically, very large, or something that is not, even if it's something that's not ending per se, it's still something you could count. But a continuous or numerical measurement, that's where we have a infinitely many possible values. It's not countable. It's something that's measured. Usually is something with, for example, decimal point values or fractions. A categorical type of variable, it's qualitative or attribute data. It names or labels, but has no counts, no measurements. So, for example, we want to know if these are quantitative or qualitative. Ages and years of subjects enrolled in a clinical trial. Well, age is a number, so this is indeed going to be a quantitative measurement. Quantitative. Genders of subjects enrolled in a clinical trial. Well, genders, those are definitely not numbers. So this is a qualitative measurement. 25 randomly assigned identification numbers. Although these are indeed numbers, these 25 randomly assigned identification numbers They are used to categorize people. It's used to give some type of order, a categorization. So because of that, it's qualitative. And adding and subtracting an identification number makes no sense. Hogwarts house. That is definitely a qualitative measurement. And then zip code. Zip code again is a number, but it's used for based on location. It categorizes where we live and assigns it some type of order. This also is qualitative. Now we want to identify if these are discrete or continuous. So each of several physicians plans to count the number of physical examinations given during the next full week. And we want to know, is this discrete or is this continuous? Well, for something such as this, especially since they're saying they want to count them, that's discrete. Might be very large, might be very small. Doesn't matter, it's still discrete. Researchers plan to test the accuracy of a blood typing test to represent the process of submitting a sample of the same blood until the test yields an error. This could be something that could be very long, and who knows when it will end. So it could be something that could be an infinitely long outcome, but still something that you could count, since you have a specific number of times that occurs. So this is going to be a discrete measurement, though it's technically not really a measurement, since you could still count it. When the typical patient has blood drawn as part of a routine examination, the volume of blood drawn is between 0 milliliters and 50 milliliters. Since this is a volume, and it could be anywhere between those two values, this is going to be continuous. And let's face it, since it is indeed volume, it could have a decimal amount. And then the number of house points Harry Potter earned in his first year at Hogwarts, that's something you could count, although something that's probably very high. It's still something that you could count. So this is discrete. Now we have 4 levels of measurement when it comes to our data sets. Those being nominal, this is where the data consists of names, labels, or categories only. Okay? Only. An ordinal level of measurement, that's data that can be arranged in order. And it gives a name, and a label, and a category. The interval level of measurement is data where differences or a magnitude can be found and are meaningful. But 0 is arbitrary. So 0 is arbitrary. But it also has an order, and names, and labels, and categories. Likewise, a ratio, that's data where ratios are meaningful. It has a natural 0 starting point that's meaningful. And it has differences in magnitudes, and order, and labels, and categories, and names. So the higher up that we go on this list, each of these levels of measurements still maintains the ideas presented below it, which is also described in this table down over here. So again, that ratio, there's a natural 0. This includes heights, lengths, distance, volume. An interval is where differences or magnitudes are meaningful. There is no natural 0 starting point. Those ratios are meaningless. So that's body temperatures in degrees Fahrenheit or Celsius. Ordinal, that's the data can be arranged in order, but the differences either can't be found or are meaningless. So ranks of colleges in the United States News and World Report. also something like zip code, for example. Nominal is a category only. Data can't be arranged in any order. Something like an eye color, dress color, that type of thing. And we want to identify the unit of measurement with these. So a yes, no, undecided question, that just names the answers. Gives no order. So nominal. A coded question like a yes, a no, a not sure, that type of thing, this is also nominal. Even though it gives it a number, per se, it doesn't really try to order it in any sort of way. A lower grade in this class, your lower grade, that is ordinal. It gives an order to it, right? Ordinal. So, like A, B, C, D, F, that type of thing. Temperature in Fahrenheit or Celsius. Note that specification. This is an interval. Level of measurement. And that's because 0 degrees in Fahrenheit or Celsius 0 degrees Fahrenheit or Celsius does not mean an absence of heat. And so because of that, that's why it's interval. Years, likewise, is also interval. That's because something that's 0 does not mean you're not born at all, or something like that. Or that, the earth or life ends or something like that. Heights of students, this is ratio. Someone can be twice as high as someone else. And class time is also ratio. You could be in class for twice as long as someone else. And a height of 0 and a class time of 0 both make sense. As an absence of height, as in no height at all. And a class time of 0 means, you don't have class. Or you skipped class. Or you didn't have class for some unknown reason. Now, with this idea of data, we have big data. And big data is a large and complex data set that requires analysis beyond the capabilities of traditional software tools. And it could have sizes such as terabytes, petabytes, exabytes, zettabytes, yottabytes, etc. And data science as a field itself, which is what most of you are probably taking when taking this course, it's an application of statistics, computer science, software engineering, and some relevant field, such as biology, epidemiology, etc. And an application of these, of using big data, are such as the flu forecasts being passed on each year, or now, especially with what's currently happening in real-world events, the coronavirus COVID-19. The forecasts of that, and how those are measured, either with respect to actual hospitalizations or whether or not someone gets a test for either the flu or the COVID-19, or an internet search of either symptoms or determining if you have it, that type of thing. The spatiotemporal epidemiological modeler from IBM. This is a variety of data correlated with disease data. Google Maps records and analyzes the GPS data from the smartphones. Likewise with internet searches, in and of itself, can be big data, just like Amazon tracking your packages. Some jobs involving big data include jobs such as a data scientist from Facebook, IBM, PayPal, essentially any business that currently operates in data. An SAS programmer or a data scientist at the College Board. A senior data engineer or scientist at Netflix. Jobs such as those. You can have a solid background in statistics and computer systems, but also in fields beyond statistics as well, which is why sometimes some of these jobs can indeed include other things, and they want you to be knowledgeable, or at least have some idea of it. That's why sometimes data scientists, they do also partner with other people as well, and other specialities to then be able to run these different analyses. But a big problem, a big problem within data science, or in collecting data in general, we could have missing data, and the missing data is not a good thing. It could be something that's completely at random. The likelihood that the data value is missing is independent of its value or any other value of the data set, meaning all data values are equally likely to be missing and it really means nothing at all. Or it's not by randomization, meaning the missing value is related to the reason it's missing. An example of a missing data is this cell on this data set down here. Notice how it's missing. Sometimes when it's missing, it could be marked as a data, just as a dot. It could also be given a value of NA, but not available or not applicable, that type of thing. Thank you.